Welcome to the second part of our lesson on structured data in Java, which deepens our exploration of the Java Collections Framework. The first part of this lesson presented a general overview of the framework, focusing on key interfaces it defines. The second part of this lesson focuses on several popular concrete classes that implement interfaces in this framework. After completing this part of the lesson, you will understand the characteristics of different collection implementations so you can choose the most appropriate class for a given problem. You will also know several important generic algorithms that work on various Java collections. Finally, you will recognize the different options available for iterating over all elements of a Java collection. In the last lecture, we discussed interfaces and how they relate to one another, but it is important to remember that an interface, as we defined it, just specifies the methods that must be provided. The interfaces themselves are not working classes that can actually do anything for us. To use an interface, we need a concrete class that actually provides all the methods specified in the interface. The classes are free to contain additional methods too, but at a minimum, they must provide the methods of the interface. These classes will still be generic, which allows them to be written once but still store data of any type. And a key aspect of all this is that there are many possible ways to implement a given interface. We might implement an interface by using a resizable array to manage the underlying storage of objects. Or we might use a linked list rather than an array. Or we might use a tree structure or a hash table to store the objects. Each of these might be used to implement an interface with their own set of advantages and disadvantages. Here's a table showing some of the possible implementations for the interfaces we have been discussing. We see that there are several options to implement a set or a list or a map. We do not have the time in this lesson to go into great detail about all these options, but in the subsequent slides we will highlight the main differences between resizable arrays and linked lists and between hash tables and binary search trees. It is important to understand their strengths and weaknesses and to think about the trade-offs when selecting an appropriate implementation. Before we can compare a resizable array and a linked list, let's briefly introduce their main concepts. We learned earlier that once an array is allocated, its size is set and cannot be changed. So how can a collection have a resizable array? Well, it can allocate a completely new array when necessary and copy all the data from the old array to the new array. If the array is large, copying all the elements may take some time. Now, a linked list stores a sequence of elements very differently. Rather than storing them in sequential memory locations like an array, a linked list stores each element in its own node. Each node has a link to its predecessor and successor. So when we compare resizable arrays against linked lists, we need to do so when considering the different operations that we may need to perform on them. Consider indexing. Arrays allow us direct access to any element in the array based on its index. That is because arrays store their elements in contiguous memory. But if we want to get to a specific index of a linked list, we need to traverse the list from the beginning. When we attempt to insert or delete an element from the middle of an array, we need to shift the subsequent elements to make room or to fill the gap. But such shifting of elements is not required with linked lists, since we can link in a new node or unlink an old node very easily. And we need to remember that a resizable array will actually need to resize when it becomes full, whereas linked lists can continue to grow without needing to make full copies of themselves. Before continuing, it should be noted that adding new elements to the end of an array is quick and efficient, at least until it needs to be resized. And if we compare the memory requirements of the two, we see that arrays only need to store the actual elements, whereas a linked list must also use memory for the links in addition to the elements. Next, let's move on to hash tables and binary search trees. First, a hash table is a structure that uses a function, called a hash function, to convert a key into an index into a table. The goal is to distribute the keys randomly over the table where we store the elements associated with the key. Thus, given a key, we can quickly look up and retrieve the element associated with it. These tables need to handle the situation when two distinct keys hash to the same location in the table. This is known as a collision. There are different ways to handle collisions, and we will assume that the table handles them for us while still maintaining fast lookup. A binary search tree stores its information in a rooted tree fashion that maintains parent-child links. In fact, each parent could have 2 child links to subtrees. And to facilitate fast searches, the tree is maintained in sorted order, with all the elements in the left subtree being smaller than the parent element, and all elements in the right subtree being larger than the parent element. This is known as the binary search tree property. Given that hash tables and binary search trees are only used to implement set and map interfaces, we will compare them on the limited operations of sets and maps. In particular, these 2 interfaces are mostly concerned with 3 issues. 1. Adding elements or pairs to the collection. 2. Looking up elements or pairs in the collection. And 3. Processing all the elements or pairs in the collection. In the case of performing an insert or lookup, hash tables give us direct access to an element or key via the hash function, whereas we need to walk a path from the root to a leaf for a binary search tree. Note that we do not need to traverse the entire tree since we can exploit the binary search tree property. When processing all the elements in a set or a map, a binary search tree allows us to process the elements in sorted order, whereas with a hash table, the processing is unordered. Please note again that it is important to understand the trade-offs between the different implementations so that you can pick the more appropriate implementation for a problem that you are solving. Once you have selected your implementation class, you should still declare your variables in terms of the interface rather than the implementing class. This increases your interoperability with code written by others, and it allows you to change to a different implementation class in the future by only changing a single line of code. For example, if you needed a set of strings and you decided that you want to use a linked hash set implementation, you should declare your collection object to be a set of strings rather than a linked hash set of strings. One final note before moving on. The collections framework also defines several algorithms that can be applied to collections and maps. These algorithms are defined as static methods within the collections class. There are methods for sorting and searching, for shuffling and rotating the elements, for reversing or filling a list, and for finding the min and max elements. To conclude our discussion of the Java collections framework, we want to address the issue of iterating through all the data elements contained in a collection so that we can process each element in some manner. We refer to this as iterating over the collection. There are several ways to accomplish this in Java, and we will address 3 in this lecture. We will consider using indexing, for each loops, and iterators. If the collection you are using implements the list interface, then you can access elements in the collection based on an index. And the ability to index into a collection allows us to use a standard for loop to access each element. For example, if you create an array list of strings and add elements to the array list, you can use a simple for loop that iterates from I equal to 0 up to the size of the array list. And then you can use the get method to access each element by its index. Now this does work, but it is not the preferred way. In fact, this style of programming can be very poor for large linked lists, since each get operation must walk the linked list all the way from the first element. A much easier way to iterate over a collection is to use the for each loop. This is the same for each loop that we saw for traversing an array, and it works in an identical manner. This is very clean and concise, and it is recommended to be used when possible. But there is a limitation for using the for each loop in that they are read-only, and they do not allow you to modify the collection while you are iterating over it. The third way to iterate over a collection is to use an iterator. An iterator is a mechanism for iterating over a collection in a generic way. All collections contain a method named iterator, which returns an iterator object for that collection. This iterator has 3 methods. The hasNext method, which allows you to test if there is another element in the collection. The next method, which allows you to access the next element in the collection. And optionally, the remove method, which allows you to delete from the collection the last element that was accessed. And here is our same example, which now uses an iterator. After filling the array with data, we call the iterator method that creates an iterator object, and we assign it to the variable itr, which is an iterator that returns strings. And then we use a while loop that executes as long as the iterator says that there is another object. And in the loop body, we get the next object and print it out. This strategy works very well and even allows us to remove elements from the collection if we desired, though it is a bit more verbose than using a simple for each loop. The great thing about iterators is that they take care of all the low-level details for us and allow us to traverse over a collection regardless of what type of collection it is. Iterators work the same for arrays, linked lists, binary trees, and hash tables. This is important since sometimes we do not know the exact implementation that we may be dealing with. But as long as we are dealing with a higher level abstraction, such as an iterator, the low-level details do not matter to us. So as has been mentioned before, we want to program to the interface rather than the concrete class, and thus our code will continue to work even if we later choose to use a different concrete class. Finally, it is worth taking a moment to note that the map interface does not provide an iterator, but a map does have two methods that return collections to us, and we can easily iterate over them. This second part of the lesson on the Java Collections Framework introduced you to some concrete classes that implement key interfaces in the framework. Now that you've completed this part of the lesson, you should understand the characteristics of different collection implementations to enable you to choose the most appropriate class for a given problem. You should also know several important generic algorithms that work on the various Java collections. Finally, you should understand the different options available for iterating over all elements of a Java collection.